Okay, thank you for extending this invitation to SkyTEM and allowing me to do it in English. My Dutch is a bit rusty. And it's also great to have this opportunity, of course, to present our technology, but also get feedback on how you see it. So it's a great pleasure to be here today. So what I'm going to do is I'm going to present how airborne geophysics can be used for different water applications. So first a little about background, the company background, then the challenges we can address, followed by an introduction to SkyTEM technology, then a couple of examples, and then some cost considerations, and finally a summary. So back in the late 90s, Denmark embarked on a nationwide program with the objective to map all the main water resources in the country using ground geophysics. However, it soon turned out that ground geophysics was too time-consuming, and it was also a logistical nightmare because you have to go on the ground. So in 2001, a research group at Aarhus University started to develop a helicopter method that could match the ground-based methods in terms of technical qualities. So after successful development of what became the SkyTEM method, SkyTEM was established in 2004 as a private company, as a spin-off from Aarhus University. So today we have 45 employees worldwide. We have a head office in Denmark where we started, and then we have subsidiaries in Canada, Australia, Africa, and UAE. So we have a global reach with our activities. We have extensive international experience, and we have worked on all continents, including Antarctica. And we work for some of the largest mining companies in the world, and also geological surveys, USGS and BRDM, the French Geological Survey. The technology is very generic, so it can be used for many kinds of applications. So our activities are split between water, mineral exploration, and geotechnical engineering. R&D has always been part of our DNA because I think we are a spin-off from university. So we constantly try to push the envelope and come up with new innovative solutions. We have a team of 8 engineers and physicists that work full-time on R&D, and this has enabled us just within the last 12 months to launch 3 new systems for different applications. And now focus a bit about the challenges we can address with SkyTEM technology. First, aquifer vulnerability. In Denmark, where I come from, nitrite leaching from the surface into the aquifer is a big issue. So mapping the natural protections over the aquifer is important. Second, we can map the aquifer size and the interconnections between the aquifers. And third, saltwater intrusion in coastal region. It is a major challenge worldwide because many of the large cities are in fact located close to the coast. So these are some of the questions we can answer with SkyTEM. Then, to give you a sense of the technology and how we operate, I'm going to show you a short video. This video was actually recorded by BRDM in connection with a survey we did on Reunion Island in the Indian Ocean in 2014. problem. So I hope it gave you some idea about what it's all about, a helicopter over the ground. So SkyTEM technology is based essentially on what is called Faraday's law of induction. So on the carrier frame, we have a current loop mounted, and we energize this current loop with a strong current. This current is terminated abruptly, which induces current in the subsurface, electrical currents. And we measure the decay of those currents with a induction coil mounted on the carrier frame. This process is repeated dozens of times each second, so we record the variations as we move. That's the idea. We can't go deep into the physics here, but the main takeaway is that we map the resistivities in the uppermost 500 meters. Before I answer the question why the resistivities are important, I'll make a short digression. We are all familiar with X-rays and that it can be used for diagnostic purposes. And it's because different tissues absorb X-rays differently. So for example, bones absorb the X-rays more than soft tissue. So we can produce an image of the human body and, for example, see if we have any fractures. So back to the questions about resistivities. They are important because different rock types and sediments have different resistivities. We have up here a resistivity scale. So if we look at sedimentary deposits, we see that clays have low resistivities, silts intermediate, and gravel and sand have high resistivities. When it comes to water, we see that salt water has a very low resistivities, which makes SkyTEM ideal for mapping saltwater intrusion. So, mapping the resistivities, we can produce an image of the 3D image of the subsurface in terms of geology. That's the idea. Then I show you this diagram of the overall processes, and it's because I want to emphasize that SkyTEM is part of a value chain that is comprised of different disciplines and also includes normally different companies, among others consulting companies. And it's because we have to remember what is important is that we want something we can use for water management, and airborne geophysics is not enough. So this overall process is composed of first, background research and planning, second, execution of the SkyTEM survey, third, ground follow-up, normally in the form of drillings, and fourth, data analysis and 3D modeling, which can be converted to basis for decision-making and water management. Then some logistical considerations. A survey area is normally covered by grids like you see here. We have flown along the green lines with a spacing of 200 to 250 meters. And then we cannot overfly buildings. And that's because there's a hypothetical risk that we can actually lose the equipment under the helicopter. Although it very rarely happens, we cannot, of course, jeopardize people's safety. So that's why you see we have not flown over this town. And then we cannot fly parallel to power lines and cables because they will distort the data. Then moving on to an aquifer delineation project we did in Nebraska. This project was led by one of our American partners, XRI Blue, which is a consulting company. XRI Blue consulted SkyTEM to do the airborne component. The main issue in this area was scarcity of water, mainly due to overexploitation, which meant that some of the domestic wells were running dry, but there was also concern that some of the municipal wells could do the same. So the main idea was to sort out the hydrogeology in the area and to come up with a sustainable water plan. So we are here in the northeastern part of Nebraska, in the Elkhorn Natural Resource District. And we have flown here in this grid shown with the blue lines. And again, see we haven't overflown these two towns. So after data connection, you always correlate the airborne geophysics with existing information, typically drilling information. So that's what we have done here. So now we have collected resistivity data. That's what you see on the vertical sections here. And we actually have a resistivity scale here. And then on top of each section, we have plotted the drilling results. And we have the lithology scale over here. So now we want to see the blue colors here corresponds to clay sediments, whereas the orange and red colors corresponds to more coarse sediments, sand and gravel. So we can see how do they correlate. In this depth interval here, where we have red colors, we see that it corresponds nicely to more coarse sediments, whereas if we have the blue colors, low resistivities, we have more clay sediments. Similarly, down here in this interval with low resistivities, we have this low plasticity clay. And then when we go to greater depths, we go into higher resistivities, and it corresponds to coarse sediments. So there's a nice correlation in this case between the resistivities and the drilling results. Then I'm going to show you another video how it actually looks like when we put this together in a 3D model. So we have this 3D model, and we have a camera that changes angle. So we look into the 3D model from different angles. So it's different slices in the model. We'll see in a minute. Then we introduce some ISO services. So hopefully it gave you an idea how we could see the geological structures in the area, and we could introduce some isosurfaces that could confine the aquifers, define the aquifers better. So based on this 3D model that's produced in this area, XRI Blue, the consulting company, they could produce this map of the aquifer thicknesses. You have a thickness scale here. and we see that it varies in the area and it's even absent in some area. Also, they could compute the total aquifer volume in the area, 131.5 million cubic meters. In addition to this, they could also point out areas where we have risk of nitrate leaching to the aquifers. So it was a quite nice study. Then we moved to Holland. We are here on the northeast coast of an island, Zelling in Holland. So we have the coastline here with the solid lines. This SkyTEM surveys was carried out as part of the as part of the Interreg project, which is a research project that is aiming at looking at the consequences of increasing rainfall that is predicted in the northeast region, and thereby rising groundwater level that will lead to extra outwash of nutrients and pollutants to the sea. So now we look at the airborne results. That's a horizontal section, resistivity section. So we have a resistivity scale down here, and we are looking at this depth interval from 15 to 20 meters. So the blue colors would be salt water we have here outside the coastline. And we see that in this depth interval, we have high resistivities, that is, we have no saltwater intrusion. If we look at it from a different perspective, we look at a cross-section here, more or less perpendicular to the coastline, and we produce a resistivity sections along this line, red line. Again, we have the resistivity scale here. We see that we've been able to map this saltwater, freshwater interface as the white dashed line, and we can see that the saltwater interface dips under the island and actually is located deepest on the middle of the island, as you would expect. So quite nice example of mapping of saltwater intrusion in a coastal area. Then shortly a bit about the survey cost, because that was one of the things I was asked about. Survey cost follows what you could call economics of scale. That is, the larger the survey, the lower the unit cost, in this case, the cost per flown line kilometer. And it's because we have some one-off costs. We have to mobilize helicopter, personnel and equipment to the area, and they are, of course, independent of the survey files. They have to be done in any case. And finally, so why do conduct a SkyTEM survey? It's proven technology and internationally recognized. It's routinely used by governments around the world. It's a highly efficient method. We can collect up to 1,000 kilometer data on a daily basis, which we did recently in British Columbia. It offers greater certainty compared to the situation where you didn't do the airborne, and it's inexpensive given that you get the greater certainty and you can optimize your effort on the ground, and also compared to conventional ground-based methods. So fly first, drill later. Thank you for your attention.
So thank you very much for a very nice presentation. Can I give the floor to any one of you? You can do in Dutch if you feel more comfortable in Dutch, then I will translate in English. Heeft iemand iets te vragen over Pier?
Can you tell me,
I need to give you the floor. Yeah, that's for
yeah, it's for.
No, it's not. It's only for the record.
Okay, okay. In order to the survey, can you explain what the difference can be and how precisely can you measure a certain layer of soil? Because in Otterschelling it was 15 to 20 meters, and in the mountains it was up to 500. But is it possible to measure the first 5 or 10 meters only?
Yeah, it's a very good question. First of all, the 500 meters I was talking about, that's the depth penetration we can achieve. So we can measure, we can get information from the surface and down to 500 meters. And the other thing was, what is the accuracy of the measurements we can do? And it depends on which geology we are talking about. That's one thing. But if I look at something very close, I can see many details, but the farther away something is, the less detail I can see. This also applies in this case. So when it comes to mapping aquifers, you get the information. You can say you have the drilling informations, and you can sort of interpolate between the drillings. That's the way you can do it. But you can't put it down to 1 meter and say it's 9 meters instead of 10 meters thick, for example. You can't do that.
Thank you.
Yeah.
Anyone else?
Yes, I was wondering if you could help, for example, mapping saturated and unsaturated groundwater bodies. And we just gave an answer on how deep and in what detail, but so you say in the top layer of the top 2 or 3 meters, you cannot differentiate between saturated and unsaturated zones and so on.
Sometimes we can, because when you have unsaturated sand, it has a much higher resistivity than saturated sand. So depending on the thickness of the unsaturated zone, you would be able to do that.
So for groundwater modelers or for the water balance in the daily practice of the water manager, you say it's not really suitable surveying technique.
Oh, it's used extensively for that purpose.
Okay.
In Denmark, we have mapped 40% of Denmark, and one of the main objectives have been to draw up hydraulic models for all these areas. And it has been part of the input to set up the hydraulical model. But you will not base it only on airborne geophysics.
No.
You will also base it on other data.
Iemand anders, ja.
What are your experiences with dense populated area? Such as Holland, you see a helicopter, we have problems with drones.
Yeah, that's another good question. That's another good question. I was taking the train from the airport, and I was looking at the train. I said, there are many places here we can't work. But in Denmark, where I come from, it's also, we have a lot of cultural noise, as we call it. We have a lot of power lines, a road, and so on. But in the open land, you can easily do it. And although you have power lines and roads, you simply cross the roads and the power lines, and you can still use the data. So it depends on the area. But I think Denmark compares very well with Holland. It's densely populated in most regions.
Anyone else? Iemand? I do. To be honest, I had one question myself. How do you deliver the results? Is it a data file? Is it a web interface? In what way do you offer the results to the clients? It's
essentially a data service. So we provide data, and as I try to explain, we are normally part of a value chain. So we would deliver it to the government agency, or we would deliver it to a consultancy. It all depends, but it comes in a format so that they can imported to many of those programs that are generally used in the industry.
And do you have relations with Dutch engineering firms or consultants that could deliver the measurements to these companies here today?
We have worked with Artesia.
Artesia, yeah. Okay. Iemand nog? Anyone else? Yeah.
With respect to data dimensionality and redundancy, I was wondering what the size of the data is depending on the area you're covering and the depth at which you are acquiring and delivering the data.
I'm not sure I can completely follow that question. What do you mean with data redundancy?
Well, we've been discussing this morning as well, that dealing with large data sets might be quite problematic. It has to be stored, it has to be processed. I can imagine that if you're covering 200 kilometers up to 500 meters in depth, that the data is huge.
Yeah,
how does that relate to size and depth?
Yeah, now I understand. Yeah, that has been definitely one of the objectives in Denmark, to develop efficient programs that could handle all these data sets. So this is something that's been going on for 15 years. So now we are at a point where we can handle all these data. And another thing that works to our advantage is, of course, the CPU power and the memory. So it's much easier today. But it was a challenge 15 years ago when we started, definitely. But not so much today. Just to add, we have just converted 15,000 line kilometers we collected in Angola starting in August. We already converted them to end results in January. So that's just to give you an idea. So it can be done.
Nog een vraag? Ja, Michel?
I wondered how you can detect nitrate, because you talked about it in the beginning.
Yeah, that's another good question. Again, in Denmark, where I come from, it was the groundwater mapping program was essentially a protection program. We wanted to protect the groundwater resources. So we want to find out where do we have large covers of clay over the aquifers. What is the thickness of the clays? Because it has turned out that the longer the travel time from the surface and down to the aquifer, the more it is have been reduced. So we measure the thickness of the cover and not the nitrate. That's what we do.
Okay. Final question, otherwise we'll wrap up. Okay, thank you very much again for your presentation. Are you still here when we'll drink coffee and maybe drinks afterwards? Okay,
yeah,
so
absolutely.
if people want to be in touch with you individually, then you're here afterwards. So that's great, fantastic.
Please come.
Okay, thank you. Please.
So, yeah, I'll just take my bag.
Sure, go ahead.
And I have to demount this one.
Yeah. Super. Oké, we kunnen weer naar het Nederlands. Dat scheelt. Wat vonden jullie van de technologie en wat vonden jullie van de presentatie? Wie wil er aftrappen? Oh ja, moet ik dit weer met... ja, dat is prima. Nee, laten we het maar even, dat praat wat...